Today we're going to be covering native string dissection and interface slicing. So the mission briefing for this day's task is targeted substring extraction, isolate interface identifiers, VLAN tags, and zone definitions from deeply nested or poorly spaced configuration lines using zero copy slicing, sanitization and normalization, strip whitespace, line endings, trailing garbage characters, and vendor-specific formatting quirks, for example, exclamation marks, comments, etc., to normalize data for downstream evaluation, and implicit structure validation. Leverage string methods dot start with, ends with, partition to rapidly classify lines before applying heavy logic, ensuring efficiency over thousands of config lines. So the technical constraints and edge cases. So the whitespace chaos. Network configs are notoriously unstable with white spacing, tabs, multiple spaces, and trailing carriage returns that can easily break naive splits. So the slicing boundaries. Out of bounds slicing in Python is forgiving, returns an empty string instead of throwing an error, but this can silently mask parsing logic failures if you aren't careful with indices. So case sensitivity, commands like gigabit Ethernet, and abbreviations like GI/0/1 or Ethernet 1/1 must be gracefully handled or normalized. And this is going to be the example target payload we're going to be using today in our examples. So what I want you to do is pause the video and try and write your own pseudocode to tackle this challenge. It doesn't have to be perfect. This is what I did on my very first try. And this took me many iterations to finally, figure out to a high level. But first thing I did was import the system tool to listen to data streams. And then the next step would be for payloads received to identify and isolate interface names. Then part B would be extract the description. And then if syntax filler included, ignore, else save. Clean up empty spaces or hidden breaks from the line using upper strip. Obviously this is not the fully completed, but again, I did multiple iterations in order to fill the entire thing. So take a moment to write your own pseudocode, and then I will break down the exact pseudocode we will be using. So hopefully you guys have had a chance to do your own pseudocode, even if it's wrong, which it most likely will be because this is the perfect version. It's just important that you get into the habit of writing pseudocode to at least get a grasp of what we're trying to build. So if I delete this, this is going to be our pseudocode for today's task. The first thing that we're going to do is initialize the pipeline streams using system standard input, loop through each raw line in the system. So we're going to have a clean, strip out of whitespace new lines and convert to a standard casing or match case insensitively, filter, skip lines that are completely empty or start with comments, classify and extract. If line starts with interface, split the line by whitespace, extract the second element as the interface name. Else if line starts with description, partition or slice the line after the word description, strip syntax fillers like the star signs, associate this description with the last seen interface name. Else if line starts with set interface or set zone, identify the vendor syntax, Palo Alto, slice out the specific interface and zone tokens based on index positions, and emit/save, output the clean normalized object mapping, interface, zone description. So I'm really excited. By the end of this, you definitely will understand what is going on. So if it sounds confusing right now, keep watching. The first thing now that we're going to touch on is the start of the theory. So we're going to touch on native tokenization versus heavy engines. So before relying on heavy tools like regular expression day 3, that's what we're going to look at in day 3. Production grade security tooling uses native Python string operations for structural classifications. Why? Performance and predictability. Native string operations run at C speed under the hood and don't suffer from catastrophic backtracking risk when handling gigabytes of streaming configuration data. To manipulate text safely, you must understand 3 core concepts: slicing, tokenization, also known as splitting, and Boolean flag inspection. Just quickly, what is C speed? So when Python hands off a task to built-in precompiled C language functions running directly on your computer's hardware. Native string operations like strip up are run at C speed. They bypass Python's slower translation layer, making them incredibly fast and efficient. The speed spectrum, language versus logic. So language layers, code speed ranges from hardware speed, raw ones and zeros, to compiled speed, C speed, direct instructions, down to interpreted speed, pure Python logic, which can be 10 times to 100 times slower because it is processed line by line. Algorithmic scales, so big O. O1 is constant, instant regardless of data size. On is linear, grows safely and predictably with data size, e.g. strip and loop. And O to the power of n is exponential, which is the danger zone. Poorly written logic, like bad regex, causes heavy backtracking, risking a RDoS, regular expression denial of service attack that freezes your servers. So that's when if the input that we're receiving doesn't exactly match our procedures in place, what's going to happen is it's going to keep backtracking, and that's what's going to create these loops and denial of service, which eventually freezes the servers. The takeaway is that the script that we are going to use uses linear ON logic running at C speed, is fast enough for massive data streams, and immune to CPU freezing RDoS attacks. In technology and security, tokenization is the process of breaking something valuable or complex down into smaller, safer, more manageable pieces called tokens. Zero copy string slicing. So slicing allows you to isolate a specific window of text by referencing its index positions. So line is interface gigabit Ethernet 0/1, print line 0:9 or 10. So this would output interface, and the other one outputs gigabit Ethernet 0/1, slices from index 10 to the end. Hopefully that makes a bit of sense. Whitespace-agnostic tokenization, split. Split without any argument triggers Python's smart whitespace tokenization mode. It treats any run of consecutive whitespaces, tabs new lines as single separator, and discards trailing leading padding entirely. So here's it in its example. So we have dirty line equals to IP, massive space, address, massive space, etc. So tokens equals dirty underscore line dot split, and it will treat this run of consecutive whitespaces as a single separator and discard trailing such leading padding entirely. Very useful. So essentially, hopefully you guys can start to see, we're getting a bunch of data in, but before we start analyzing and doing things with this data, we want to make sure that it's nice and consistent and readable and doesn't bypass any security measures by doing so. Boolean line classification starts with and ends with. Before processing a line, your script needs a fast gatekeeper to determine what kind of infrastructure line it is looking at. The functions do direct substring comparison checks that return a strict true or false. Network use case, quickly dropping comment lines, for example, exclamation mark, or identifying target blocks. Interface set zone. Efficiency note, you can pass a tuple of strings to start with to check multiple conditions simultaneously. So if we have the line set zone DM demilitarization zone network layer 3, if line starts with set zone, set interface, print processing Palo Alto firewall rule. So what is a tuple of strings? It's a fixed ordered collection of text values locked inside standard parentheses, A, B, C, instead of square brackets. The golden rule, immutability. Once created, you cannot add, remove, or modify items. Trying to change a value, tuple 0 equals new, will immediately crash the program with type error. Why security engineers use them? It provides a read-only lock. Use a tuple for permanent system rules like a hard-coded list of approved ports or critical admin names. So a malicious exploit or coding bug cannot tamper with them while your script is running. When to switch, use a list if the data needs to change dynamically, like logging new blocked IP addresses in real time. Final piece of theory we're going to touch on is direct partitioning. So the partition function. When extracting descriptions, you often want to split a string once based on a keyword, preserving everything after it. So a partition separator splits a string at the first occurrence of the separator and returns a 3-tuple, before separator and after. Network use case, splitting a description rule cleanly even if the description itself contains spaces or configuration syntax symbols. So here's the example. We have this line, before, sep, after, line partition with the separator being description. So print after.strip would output after the description, which is all this bit here. And there'll be another case example later on as well. Edge cases to watch out for: state preservation, context tracking. So the problem, network logs or configuration files are written sequentially. A line might say description core link, but it won't repeat which port or interface that description belongs to. The solution, your script must use a state variable, a temporary memory placeholder, to remember the last interface name it saw. When it encounters a description line, it uses that stored name to correctly pair them together. Vendor divergence, format flexibility. This is also a key point, so you might want to pay attention to this. The problem, different networking hardware writes configuration files in completely different styles. So we have Cisco style, which uses a nested multi-line block. E.g., the interface name is on line 1 and the settings are indented underneath it on lines 2 and 3. Palo Alto style writes the entire configuration as a single absolute path on a single line. So the solution would be your string parsing logic, partition, split, etc. must be smart enough to recognize and process both layout structures simultaneously without crashing. So test yourself. This is the skeleton of the code that I want you guys to try and do for yourselves. Have a read through it yourself. We start with the import sys. We have this part here where we define the function pass_infrastructure_config. I'll just quickly explain that as well. So how it works, so we already touched on in the previous episode in this series, formatted string literal. So the F tells Python to evaluate anything inside curly braces as code or variable instead of literal text. The less than 30 modifier, this is a layout engine tool. It tells Python allocate a static window exactly 30 characters wide, put the text inside this window and left align it. Fill any remaining leftover space with invisible padding spaces. The pipe symbol, because it sits outside the curly braces, Python prints it literally as a structural divider column. And then we have the print and the times by 65. This is a string multiplication. Instead of typing out 65 dashes manually, Python dynamically repeats the dash character 65 times to create a clean uniform underline for your table. So the terminal result is when this code executes, instead of the text bunching up awkwardly, your viewers will see a perfectly proportional console output table ready for incoming live data. This ensures that no matter how long or short the interface names are, for example, a tiny gigabit GI0/1 versus a massive gigabit Ethernet 0/1/0.103, the columns will always stay perfectly straight and professional. So the factory breakdown, this is very important for why we are creating this function. When you write def pass_infrastructure_config, you are building a custom data processing machine. Inside this machine, you have a series of steps. Step 1 is the sign. Print and formatted column headers, interface pipe mapping. This happens once at the very beginning. Step 2 is the conveyor belt. Start the for raw_line and system standard input, loop to grab data streaming in from the terminal, which we'll cover in a second. Then with step 3 is the sorting logic. So use your .strip and start with and split tools to clean and look at each line, which is essentially the main part of what we're trying to do in this mission. And then the output is to print the matching pairs cleanly under those columns we created in step 1. So by wrapping all of this inside of def pass_infrastructure_config, you can run this entire multi-step process anywhere else in your script simply by calling its name. The next thing is current_interface equals none. So this was a little bit confusing when I first looked at it, but essentially in network configuration files, data is structured in blocks, but Python reads files one line at a time from top to bottom. Once a line passes by, Python completely forgets it. Because of this, an issue arises. When your script needs a Cisco configuration block like this, on line 1, the script sees the interface name. However, on line 2, the script sees the description, but the interface name is gone. So current_interface is a state variable. It acts as a memory slot When your script encounters a line starting with interface, it saves that name inside current underscore interface. When it moves down to the next line and reads the description, it looks at its memory slot to remember exactly which interface that description belongs to. Next, we have for raw underscore line in system send input. So the raw information we're getting in. Clean line is just the raw line with a strip, which we touched on in the previous video. And then upper line is just the clean line with the upper. So all in uppercase. Then we have if not clean line, or clean line starts with this exclamation mark, continue. So what this essentially means is that if not clean line, that means it's blank, which means it's all good to go. Or if it's clean line and starts with this exclamation mark, anything outside of that, continue. Pretty self-explanatory. Then we have the if upper underscore line starts with interface. We'll go into this. To do, you need to tokenize the line and isolate the interface name. Use whitespace-agnostic splitting, which we touched on before. Task 3 is to pass out the descriptive payload. So upper line starts with description. And then the final to do is to extract interface mapping records from absolute lines. Then we have this bit at the bottom here as well. This is standard Python design pattern called execution guard. It controls how the script runs. Every Python file has a built-in hidden variable called __name__. If you execute your script directly from the terminal python 3 parse_config.py, Python assigns the string to that hidden variable. The condition passes and your function runs automatically. If you or another program try to import this file as a module into different script, import parse_config, name is set to the actual file name instead. The condition fails, preventing your script from running its main logic automatically when you only wanted to borrow a function from it. So it ensures your code safely acts as either a standalone automation tool or a reusable library module without crashing or running unexpectedly. So this is very important when we eventually integrate this into a larger log parsing system. So have a go for the final code for today, taking everything that we've done into account. Pause the video now, try and write the code out for yourself. Okay, hopefully you've had a crack. Now we're going to go into the final code. Just a quick note on this top line, why it's there. It's called a shebang. What is it? It's a specialized instruction header placed on the very first line of a script used by a Unix-like operating system like Linux, Mac operating system. So the problem is when you run a script using .parse_config.py, the computer's terminal doesn't inherently know what programming language the file is written in. So the solution is the shebang tells the system kernel, do not run this as a default shell script, pass this entire file to the interpreter path listed right after these symbols. So why do we use this user bin env Python 3 specifically? Portability and defense. Instead of hard coding a rigid path, which breaks if Python is installed somewhere else on another engineer's machine, using env tells the operating system to dynamically look up where Python 3 is currently running in the user's active environment. So the first task that we had to do was sanitization and normalization. Which was already done. So the first task that you had to do was task 2, which was to identify if a line introduced a new Cisco interface and extract the interface token and update the state tracker. So how it looks like is tokens equals to clean_line split. If the length of the tokens is greater than or equal to 2, current_interface tokens equals to 1, print current interfaces, and then initialized. So to make sense of this, the list index slicing inside the code blocks, remember that when you call split, Python slices the text by its whitespace segments and converts it into an index list starting at 0. So essentially, this is what it will kind of look like. And the length of tokens greater than or equal to 2, this is a defensive condition that verifies the line actually contains an interface identifier name after the keyword to prevent throwing a breakdown out of bounds index error. Tokens 1 targets the second item in the zero index list, isolating the exact string name of the active interface and saving it to the tracker. Cool. So it'll print out this with initialized. Second and third task that we had to do was identify description lines, strip out syntax fillers like these star symbols, and pair it with the current underscore interface state tracker. So this is how we do it. We had before separator and after equals a clean line dot partition description. So this is the example I was talking about earlier. And then we have clean line equals to after strip with the star sign and then strip again. With current interface, print, fprint, current underscore interface, and then the description with the clean description. So the partition function divides a string into the clean three tuple at the first instance of the argument token. So this is kind of what it would look like. We set the description as the second tuple. So after captures the everything remaining to the right of the side of the split marker word, which we set as description. So for the strip, this chain behaves like an onion peeling process. The first strip removes the leading white spaces, padding. The second strip drops out the outer structural syntax symbols, like the star signs. And then the final strip eliminates any interior padding remaining right next to the characters to leave just with the plain text of demilitarization zone, DMZ, -production -zone, link to core. How it fits together? When you call before, sep after, Python forces the middle variable to hold the exact delimiter you split on. So before is everything before the separator. The separator itself, in this case, is the string description. After, everything after the separator. The final mission you guys had to do was identify, slice, and map the firewall configurations cleanly. So this is how we did it. So else if upper line starts with set, tokens equals to clean underscore line split. If zone in upper line and length of tokens is greater than or equal to 6, the zone name is the third item, and the interface name is the sixth item. Print the interface name and then the zone name. Else if the interface in upper line and IP in upper line and length is greater than or equal to 6, interface name is the second token, or second token, and the IP address is the fifth token, which is the sixth item. Print f interface name, IP, and then IP address. So the firewall bundle their target rules into absolute structural configurations on individual lines requiring specific coordinate targeting. So we have zone name equals token 2, interface name equals token 5. So by enforcing a structural check verification constraint length, we safely know exactly where the value resides. So token 2 reliably extracts the zone target string, so DM zone, and token 5 maps it to the respective interface. So for the second part of that, the IP policy mapping, when passing the IP configuration line format, notice how the data shifts positions. Here, the target interface name relocates to token 2, while the network IP address perimeter is extracted from token 5. Yeah, utilizing simple index tracking logic allows you to handle both variations flawlessly without relying on complex regular expression engines. So thank you very much for watching this video today and the second day of the series. And again, just a reminder, the week 1, we are working on the core scripting, automation, and logic. Thank you very much. See you in the next video.